Serhat Can.
Thank you. Welcome everyone. Welcome to the last talk of this event. It's been great for me. I hope it's been great for you as well. Thank you for all the organizers. I myself, I'm also a DevOps Days organizer in Istanbul, and it's really been a great event. So we are not going to talk about magic, but I think for most people, serverless is still magic, right? Is anyone here used AWS Lambda or any other serverless tool before? Cool. So who is familiar with AWS? So I'm gonna try to explain some things. Okay, cool. About half. So before I start, I made this presentation before in DevOps Days Amsterdam, and after I made the presentation, some people said, "Do you hate serverless? Do you hate AWS Lambda?" So it's not the case. I actually advocate for serverless in many different meetups. I organized a serverless meetup in Turkey. But the thing is, just like any other tool, like Kubernetes, whatever it is, it can be Kubernetes or whatever you use, it has its flaws, and we need to talk about them as well. And there has been a lot of fuzz around serverless, and today I will try to show you our experience, and especially the bad parts, because we don't talk about them that much. So this is the story of OpsGenie, my company, not my company, the company I work for. We are getting acquired by Atlassian, so I might not give this presentation again because things are going to change internally. The stake might change. But what we do is we are an incident management platform for operating always-on services. So what I mean is that when people have problems, so we are the ones that help them solve the problems faster. Obviously, this means that we have probably a bit high reliability and availability requirement than most of the applications. So we know how hard it is to run those services and how hard it is to keep all those services up and running. That is why actually we decided to give AWS Lambda a serverless computing solution a try. So since 2015, engineering grew from 3 to 60. Obviously, this is huge, and this brought some problems. For example, it slowed down development. We had a lot of engineers. It was hard to release new things, and also it meant more idle capacity because we had a monolith. So we decided to break down the application into microservices. And because we had some experience with serverless, especially AWS Lambda, we decided to also try a big new feature, develop a big new feature with AWS Lambda. And most of the things I'm going to talk about today will come from this experience. So when we started, so AWS Lambda actually markets its product as, I think, this. So we wanted to have, here's my application, run it for me where I want it securely. But obviously, we don't expect to have the option to choose where. We decided we are going to go full with AWS, and we are comfortable with this decision, and it's okay for us. And for those of you who don't know, the promise of AWS Lambda is like this. This is how AWS Lambda works. So you write your code, you upload it to AWS Lambda. It can be a zip file, it can be a jar file, for example. And you set up a trigger. It can be 20 plus different AWS services. For example, it can be an API gateway service, which helps you create HTTP endpoints. It can be S3, and you can trigger a Lambda function once you create a file in S3, Object Storage Service of AWS Lambda, for example. It can be many different other services. And once you trigger your AWS Lambda function, it will run and end after some time, and you will only pay for the time your code actually runs. So this is powerful stuff. And you will only pay for that time. So let's talk about our journey. In 2015, we started writing small-scale custom integrations. What I mean is that we helped our customers integrate with OpsGenie using AWS Lambda. And this is one of the perfect use cases because they're not getting a lot of alerts all the time, and once they do, they have a bunch of them. And AWS Lambda can scale immediately in a short period of time. And also, you're not going to pay if you're not triggering the function. And also, it's easy to write a script and upload it. So this is very powerful, and actually we still use this approach with our customers to help them extend OpsGenie with some custom code with their services, whatever they use. And in 2016, we saw the first production usage. So we started to leverage AWS Lambda internally, not just with our customers, basically using things with things like asynchronous jobs, things with something not business critical, for example, with DynamoDB autoscale. So obviously AWS has some sort of autoscale, but it doesn't work the way we want it to work. So we have something custom built, and we use AWS Lambda for this stuff because it makes perfect sense. It's easy to deploy. It just runs when we need it to run, and this is actually these use cases, especially for operational things, AWS Lambda is perfect, and we are still going to continue using it. And in 2017, we wanted to go a little bit further, and a new feature called we wanted to use host a new feature called service and incident management fully on AWS Lambda. This is a customer-facing feature and integrated with the rest of the code base. And in 2018, with all the needs we had developing service and incident management, especially monitoring needs, because it's really hard to monitor what is going on within your function. So we ended up building something internally, and at the end, it's now a separate product. Actually, it's now a separate company outside of OpsGenie, but it's built within OpsGenie. It's called Tundra, and I'm going to talk about this as one of the pitfalls in the monitoring part of my talk. So I want to mention two important things about our stack. If you tried AWS Lambda, probably you know that Node.js and Python is kind of the norm, especially Node.js. Not many people use AWS Lambda with Java because it has downsides. But we wanted to, so we use Java everywhere within OpsGenie. That is why we wanted to continue using it. That is the most important reason. So that is something I think of as a disadvantage for us. And the second one is we use a lot of different AWS services. What AWS actually markets as calls serverless. For example, our entire database is on DynamoDB. This means that we don't have to manage all those connection pools of relational databases within AWS Lambda environment, function environment. So it's easy to use tools like DynamoDB and SQS and talk with them through HTTP within Lambda function. So this is one of the advantages we have. So if you have some sort of relational database, it's going to be probably trickier for you. But we also use Redis, so we also have experience with this. So now we are going to talk about the bad parts. So we have 4 of them. So the first one is cold starts. So how many of you know what a cold start is? Okay, cool, very cool. But for those of you who don't know, this is how AWS Lambda works in a very high-level diagram. These are all invisible to you. So you are not seeing any container. Directly, you are not dealing with any containers. You might see a sign of existence of a container within CloudWatch logs, but that is all. You are not controlling any containers. It's all managed by AWS. So when you call a function, when you trigger a function, then serverless, if there's no container available, it will create a new container. Then there's some initialization part, and at that point, there's a latency. This is what we call cold start. So if there's a latency, if there's no container available, if there's any initialization, there's cold start. But once the execution is completed, AWS is not charging us anymore, but it can keep containers available, and so that we can reuse them later. And in that case, we are in hot start mode, and it will run faster. So it depends on a lot of things, like AWS can kill containers and can keep them for a while. It's not something like certain, but sometimes we experience cold starts, sometimes we don't. It depends on a lot of things. And then we can, so yes, so what affects cold start? So there are a couple of things. The first one is memory size. So with AWS Lambda, you can choose different memory size. You can assign different memory size to your functions, starting from 128 megabytes to 3 gigabytes. And this is a huge effect in cold start, and we are going to see this soon in a graph. And So if you increase memory size, CPU increases proportionally. This means that initialization takes less time. And code size has a huge effect. VPC, virtual private cloud, has a huge effect. Most of the time, it doubles the code start time. So also, if you are doing something that requires CloudPath scan, it will increase the startup latency. For example, we were using Spring Framework, and it really increased the latency. And obviously, the language choice. So let's talk a little bit more about the language choice. So for Python and Node.js, it's over there. So you can't even see this. So it's probably negligible for many applications, but for Java and C#, so that we have more languages now, but for Java and C#, it is over here. So it is, for this experiment, for this application, it takes like for 100 to 28 megabytes RAM, it takes 5 seconds to start any function. For us, with 1 gigabyte, we even saw 10 seconds. Then we did a lot of optimization. So language choice has a huge effect. And what is wrong with why do we care about this? Simply, the basic premise of serverless is to reduce the operational things and focus on the application. But with this, we actually start caring about an operational concern, which has nothing to do with us. This is obviously not ideal. And obviously, if we have a customer-facing application, if user experience is important, then there's going to be some frustrated users. And if you increase memory, you are going to pay more money. And if you have multiple functions calling each other, obviously you should have some sort of asynchronous way of communication between those functions. But if code starts coming and if it's chained, for example, it takes 5 seconds. It takes 5 seconds, and it can really take a lot of time. And some functions can time out, and then in that case, your user will get an error. So what are the solutions? We talked about like why this is bad, what affects cold starts, but are there any solutions? So one thing I recommend is if it is not a big deal for you, just don't try to fix it. And this is also what AWS recommends. And one thing you can do, this is also something we did, you can just increase memory and pay more, but it will be a lot faster. If you are not paying, like you don't have a lot of requests coming through, it's the easiest way to just reduce the cold start time. And you can write your own lightweight application framework. There are not much like frameworks right now because it's still developing. But we ended up writing our own, which is something we didn't want to, but we kind of had to. But you can do that as well. And also, what you can do is you can do some smart warm-up. So what I mean by smart is that you can think about many different things to keep some containers alive. And you can do like regular requests to Lambda functions and try to keep some containers alive at the end. So there is something. So I will share my presentation from my Twitter account, and especially this blog post has all the details and will help you how to do some warm-up. So the second one is scaling. So as you know, one of the basic premises of serverless is that it scales infinitely, but obviously nothing scales infinitely. And let me show you with some concrete examples. Yes, functions scales. So for us, it scaled very nicely for some time until they don't. So there are two limitations that you need to be aware of. So the first one is what AWS Lambda calls account level concurrent execution limit. This is basically saying that there's a limit that will block your functions at some point. So this is like saying you have this number of EC2 machines and you can't have more. This is pretty bad. This is how AWS Lambda calculates the account level concurrent execution numbers you use. For non-stream-based events, but I'm assuming most of you are using non-stream-based events, and stream-based events are easy to calculate, like per shard based. But for non-stream-based events, you calculate this with this formula, and this formula says events or requests per second with, multiplied with function duration. So for different regions, AWS Lambda gives you different account level concurrent execution limit. For example, for some regions it's 3,000, for some regions it's 1,000. And if you are getting 100 requests per second and one function is taking, let's say, 1 second, and you are consuming 100 of your 3,000 limit. But if you have some sort of problem, if your function is taking like more time, maybe a third-party tool you are using is having a problem, and then it might affect you as well, because then according to this calculation, so you are still getting, let's say, 100 events per second, but your function duration increased to, I don't know, 10 seconds, and then you immediately start consuming 100 concurrent execution limit from your limit. This calculation makes it really makes it hard to deal with peaks in request numbers. For example, if you have some sort of Black Friday, you can request an increase from AWS Lambda, and there is no limit, so you can just keep asking for an increase, but they will review it, and it takes about a week for them to review, and there should be a justification. Like, you can't just ask them and they will not just increase it to 50,000, let's say. So during Black Fridays, you need to think about this, for example. And also, functions affect each other's scalability. What I mean is, in the last case I talked about, like if some function is having a problem, it can consume all the concurrent execution limit and affect other function scalability. This is actually something we had. So we had a problem with a third-party tool we are using, and then that function's latency increased, and it ended up consuming all the concurrent execution limit, and other functions we have started getting throttled. Obviously, this has nothing to do with that function, but the other functions, but it affected all of them. So to solve this problem, AWS introduced another limit. This is called function level concurrent execution limit. So if you have non-critical functions, you can just say this function can only scale to 100 concurrent execution limit. But the problem with this is, if you have 1,000 concurrent execution limit, and if you assign that function 100, and then you will end up with 900. The other functions can only use 900, and even if you are not using that 100, that's just going to stay there. And you can't just, this means that you can't just keep assigning this limit to functions however you want. Another thing you need to be careful about is that although it has some security benefits, and we kind of had to use it because we have some resources that we have to put in within VPC for security, but to be able to access those resources, we needed to put our Lambda functions within VPC. And then we have two more restrictions to scale. First, you need enough IP addresses in your subnet. And the second one is you need enough elastic network interfaces to scale. And this gets a little bit more interesting here, because normally we had 300 concurrent execution limit, but so the ANI capacity we need is calculated like this. Concurrent executions you have, so 3,000. And we use most of our Lambda functions, almost all of them, with 3 gigabytes, the top number. So this is one. So we needed 3,000 ENI capacity to be able to keep up with what we already have. But the thing is, AWS Lambda gives you 300 by default. So you need to again go them and ask them if they can increase this limit. And one of the interesting things is that you can't just see this in logs, so you have to use magic. This is taken from AWS Lambda's documentation. I want to read this. If your VPC does not have sufficient ENIs or subnet IPs, your Lambda function will not scale as requests increase, and you will see an increase in function failures. AWS Lambda currently does not log errors to CloudWatch logs that are caused by insufficient ENIs or IP addresses. So we had to spend like 2 days to talk with AWS customer service, to figure out what is wrong with our scalability once we put our functions within VPC. And simply you either have to read the whole documentation carefully, or if you encounter something like this, you have to talk with the customer service. So I'm going to go a little bit faster. So the third challenge is observability. Fixing this, it is slow. So basically monitoring AWS Lambda is harder. Why? Because there are too many moving pieces. You are not just dealing with a couple of microservices or just a monolith. If you are, if you know a little bit, like if you know more about service architectures, you might end up with like hundreds of functions, and obviously hundreds of different maybe like triggers. You might have, you can have a lot of things. And there's no way to attach an agent, so normally we use New Relic, so we could just attach an agent and do application performance monitoring, but we can't because there's no way to attach an agent. We don't have access to JVM parameters. And even how to send the monitoring data is a discussion point. What I mean by that is you can send the monitoring data within the function with HTTP, but then if it takes longer, your function will take longer, and if it fails, obviously your function might fail. And for production, with Tundra we do asynchronous, so we write everything to CloudWatch, and then another Lambda function listens to those CloudWatch logs and sends the monitoring data to Tundra. But the problem is it costs more because of the CloudWatch logs costs, and it takes a little bit more time. And for development, we directly send the HTTP requests. So what we needed also was determine the latency in different levels. We needed automated instrumentation, so we couldn't just keep writing everything we collect manually. It will be a lot messy. It is a messy thing, obviously. And we needed more metrics, so CloudWatch gives you some simple metrics, but it's not often enough. So we needed to collect like something like garbage collection counts, thread counts, durations, CPU usage details. In case of an error, we needed to get the stack trace and drill down. And one of the best things is we wanted to see all the logs, traces, and metrics all in one view. So this is what we developed, and it's now a separate product. Like if you're interested, it's not it's not the company I work for now, but I really like the product. So the last challenge was the event-driven nature of AWS Lambda. Has anyone got any unexpected bill from AWS? A couple of folks. So we did get one because of AWS Lambda. We did get an incident, like we did get a bill for $40,000 for a development environment account. So obviously we had like most of this was our problem. It was our like this was because of us. But the thing is, this was also because we weren't used to using such event-driven environments. So this was the case that we had this incident. So there's this function. This makes a request to Graylog, and Graylog is down. This is a development environment, so we don't have really monitoring. And request fails, and after 5 minutes of trying, the maximum amount of maximum time you can have, and then it fails, and there's this dead letter queue. So this is the feature of AWS Lambda. So if this fails after 5 minutes, and then the payload is sent to the queue, and there's another function pulling this queue and calling this function again. So it kept running. It consumed all the concurrent execution limit for 2 weeks, and we accidentally found about this. And then, so we got the 60% of back from AWS, even though we used it. So it's kind of nice of them. Lessons learned. So in a serverless environment like this, you need to avoid infinite retries. You can't just do infinite retry in AWS. And if possible, you need to set a short timeout. And you need to monitor and alert for pricing. Even though there is no pricing for like specific AWS Lambda functions, you can monitor the whole account and create an alert if you cross a threshold, for example. And you need to think about CloudWatch costs and sample logs and metrics if possible, because we were sending a lot of logs, and CloudWatch was like 40% of those costs was from CloudWatch. So CloudWatch is expensive, probably sometimes it's more expensive than AWS Lambda. So you're not just paying for AWS Lambda. It can be, it might seem like it's nothing, but you are going to use a lot of different services: DynamoDB, SQS, SNS, AWS, CloudWatch. And the final one is functions will be triggered more than once. So this is actually written within the AWS Lambda documentation. So simply they say that you need to design your functions to be idempotent. This happened like to us a lot of times. Even we experienced, like probably they had some sort of incident and they called the same function with the same payload 7 times, even though it's successfully completed. So we like often see 2 or 3 times like calling the same function with the same payload, even if after successfully executed. So what we do to make sure is that we have Redis. So we, before executing each function, obviously AWS has this request ID, unique request ID, so you can just check if you already processed this request successfully or not. This is our solution to this problem. So I really like this from Stakery CEO's. This is a slide from Stakery CEO. So this is a passage from AWS Lambda's feature page. And the correct version should be, AWS Lambda invokes your code sometimes when needed and can scale to support certain rates of incoming requests, but requires you to properly configure everything. There are limits to the number of requests your architecture can handle. I really like this. So obviously, so I talked about the bad things today, but there are a lot of like great things about AWS Lambda. So we're still using AWS Lambda for many, many things. But these are our experiences, and there is reality in this one. And at the end, obviously it is either Kubernetes or AWS Lambda, whatever it is. I really like this quote from Bridgette. She says, I really recommend you to read this article if you didn't read it. It's called "Containers Will Not Fix Your Broken Culture." And she says, tools can and do help, but they can't make us care. So it is up to you to care about the tools you use, and it is obviously some part is AWS's responsibility, but at the end it's your responsibility to care about whatever you use. So thank you. That's all.
So is there any questions?
We can also talk about, like if you have a question, specific question.
So you say that there is ways to actually keep the containers alive, so you don't need to have this waiting time for the call startup.
Yes.
How do you handle that? And how do you handle that actually the containers are not used by someone else, the ones that you are keeping alive?
So basically, if you make, so you made a request and your function runs, and if you make another request, if it's already running, and then AWS creates another container. And if you make 10, let's say 10 requests at the same time, AWS will create 10 containers at the same time. And normally it keeps these containers, like it's based on like their internal logic. So what our experience is that they keep containers like 5 or 10 minutes before recycling them. So if you make 10 requests at the same time, you will have, like after the execution completes, you will have 10 containers waiting for you for 10 minutes, let's say. So that is how you can keep some containers alive for the next calls. But this is like what we do with Tundra. So we have this, so you don't just implement AWS Lambda's interface to implement Tundra's interface, and then Tundra has this protocol which knows like there's another Lambda function, and you can say that this Lambda function should have this number of containers up and running, and then another Lambda function makes a request, and that Lambda function just ignores those requests because it knows that this is just a warm-up request. So it's there's some sort of protocol between those Lambda functions that we implemented.